This was the straightforward part of today's class. Straightforward because if you think about what we did, right, in this hour, was really just transposing to rule induction what we knew about decision tree induction, right? It wasn't that different at the end of the day. You might even wonder if this was all, worth all the trouble, since if you already know about decision trees, then figuring out how rule learning works is not that big of a deal necessary. Okay? But now we're about to take a big leap into something much more powerful than anything that we saw last time. And in fact, a large part of the reason why we've looked at rule induction the way we did so far is that is going to be the basis for learning rules of a much more powerful form. Okay? And that's what we're going to spend the rest of today's lecture on, is learning first order rules. I don't know if you guys know this nomenclature, but everything that we've seen so far was propositional representations because they're at the level of propositional logic. In propositional logic, all that you have is propositions, like a Boolean symbol is a proposition. The Boolean symbol A represents it's sunny today. Okay? And you can do a lot of propositional logic, but it's also a very impoverished language. To really do programming in general, you need something at the level of first order logic. First order logic is when you can have functions and arguments to the functions and predicates with arguments and so on and so forth. We want to learn things like that, right? This, of course, is much, much harder, but actually at this point, step by step, we're already halfway to that. So let's see what else we have to do and what this new, more powerful representation is. Okay? So there's a lot of formal background that you could give here about first order logic and whatnot. I'm going to mostly avoid that and keep things at a more or less intuitive level. However, if at any point you're not clear what we're saying or have any questions, just let me know and we can look into things a bit more carefully. Okay? So I'm going to be relying on examples a lot to show what happens here. So here's a classic example of the type of thing, very simple, that you can learn with first order rules, with rules in first order logic that you couldn't learn with proposition rules or with decision trees the way we saw before. And this is the example of the concept of ancestor. Ancestor is not a property of a person. It's a property of a pair of people. And this is what makes it interesting. Whether a patient has tuberculosis or not is a property of that patient. Whether Anna is an ancestor of Bob, well, that's a property of the pair. Right? So things now get a lot more interesting. And what we would like to do, right, is learn the definition of ancestor from data. Right? You give me a database of family relationships, and I want to infer from that what ancestor means. Right? This is a very real example, right? I have a big information extraction system. In fact, we're going to see an example from information extraction shortly. And I want to, extract these relationships, figure out, how one, relates to others, and so on and so forth. Okay. So here's an example of a couple of logical rules that define ancestor. One is X is an ancestor of Y if what? What's the simplest case in which X is an ancestor of Y? Think of this as a recursive definition and think of the base case. What is the base case of the recursion?
Parent.
Parent, right? X is an ancestor of Y if X is a parent of Y, right? So that's our first rule. Right? Easy street. What is the more interesting case, the recursive case? X is an ancestor of Y if? What is the general case? Right?
If X is a parent of another ancestor of Y.
Exactly. If you are a parent of an ancestor of somebody, then you are also an ancestor of that somebody. Everybody agree? And that's what the second rule here is doing. X is an ancestor of Y if there's a Z somewhere such that X is a parent of Z and then Z is an ancestor of Y. Okay? Look at this carefully for just a second because this is the kind of argument play that we're going to be using all along here. Right? This here, some of you might know, this is actually a couple of statements in data log. And SQL at some level of abstraction is equivalent to data log. And so most of the database, or at least the simple database queries that you issue, can be formulated in this form. Data log is also a special case of the Prolog programming language. In Prolog, you can write whole programs just by writing down rules like this in logic. The difference between Datalog and Prolog is that in Prolog you can have functions inside here. I could have ancestor f of x, y. We're not going to deal with that case here. We're just going to look at the Datalog case. because it's complicated enough and powerful enough for our purposes here. Okay? So what we would like to do is learn a couple of rules like this from data. And by the way, these rules look a little weird because the arrow is pointing in the opposite of the usual direction. We have the antecedent first and then the consequent, but this is what people do in prologue and data log, so we're just going to stick with that. Okay? You can read this rule any way that you want, but the golden rule is the consequents are always on the back of the arrow. The consequents are in front of the arrow, and the consequents are behind the arrow. Okay? So this is the type of representation that we would like to be able to learn it. Might be much more powerful than what we had before. Okay? Now, of course, this is a trivial little example, right? Just family relationships. What's a more realistic example of this? Why do we care? Right? Here's actually a real example of the type of first-order rule that you can learn. Let's suppose that you want to do the ever popular thing of classifying web pages. You might want to classify web pages by, what topic they're on, by what kind of object they represent, right? You can see how this would be interesting to a lot of companies like Amazon and Google and Microsoft and whatnot, right? You want to organize the web, right? So here's an example of such a rule from a real system, and we're going to see how that system works shortly. They applied this system to the web pages of a bunch of computer science departments, and they wanted to classify the web pages into this is a course page, this is a faculty page, this is a student page, this is a project page, and so on. Okay? So I'm trying to figure out if a web page is the web page of a course or of something else, right? And now what we're going to do is we're going to do rule induction, right? We already know how to do rule induction. We're going to try to form a rule that predicts that something is a course page using properties of the page. Okay? So what rule, this is the single most accurate rule for predicting courses that come out of the system, and let's see what it had. Okay? So it says that A is a variable, A is a course. This is how you read a rule like this. What does this first antecedent say if you translate it into English?
Web page A has the word instructor.
Right. So if the web page contains the word instructor, that makes it more likely to be a course page. Pretty obvious, right? And what does the second one say? By the way, this thing here, in case you're not familiar with it, is the negation sign, right? It means not. So what does this one say?
Doesn't have the word. It's good.
Okay, let's keep moving and not focus too much on what that part of the rule means. Right? I don't know. A course page is a course page if it doesn't contain the word good in it. Well, this is just an empirical fact. Let's not overinterpret it. Okay? But anyway, these two antecedents actually we could have done with what we had before. Right? In fact, people often do this. I represent a web page as the bag of words that appear in it, right? It contains the word instructor, it does not contain the word good, it contains the word this and that and the other, right? And then I could just have the rule that says, well, if instructor not good, then course, right? So far, propositional would be good enough. Okay? Where does the extra power come in? Well, let's see the next pair of antecedents, these two. What are these two saying? This is the really interesting part of this rule.
If there's a link from page A to page B, and page B includes the word assign.
Or contains the word assign.
Yes.
Right, so by the way, something that people often do in text processing is stemming. Stemming means that I cut out, the suffixes of words. So this assign really comes from the word assignment. Right? So what these two guys are saying together is that something is a web page if it points to another page that contains the word assignment. Well, of course. Isn't that brilliant? The web pages for courses contain links to pages that contain the word assignment because they are assignments. In fact, the web page of this very class is a positive example of this rule. We really contrived it to make that happen, but hey, we have that positive example, right? It does contain the word instructor, it does not contain the word good, and it contains a link to a page that says assignment. Right? See? This is the power of machine learning. Isn't it amazing? Especially when you contrive the examples. No, just kidding. Okay, so see why this is different from what we could do before, because now we're talking about a property of something else. We're no longer talking about properties of the object that we're classifying, this web page. We're talking about properties of a related object. And now we have all this power at our hands, right? And you can see why in the web you'd be able to go hog wild with this, because links are all over the map, right? This page is about something because there's another page that points to it that's about something else, etc., etc. Right? So now I can use here's another powerful example of this. I can predict that you will go see this movie if your friend that you trust went to see that movie. Right? Now I can use properties of related objects to predict properties of the objects of interest. I couldn't have done this before. Or maybe I could have done this by putting together in the record for an object all the properties of all the related objects, but this is insane, right? It would mean like that for every page that I'm trying to classify, I would need all the properties of all the pages on the web that are connected to it, which is probably all the pages on the web, or almost all of them. So that would be a non-starter. Okay? So we get a lot of power from being able to do this. Now, by the way, what is this last one here? What does this mean?
He has a link.
This is actually the least obvious one, but it also makes sense, right? So this here says not link from BC. What is this saying in English?
Nothing links to page B.
Actually, the other way around. B links to nothing. Remember, links from A, B is A links to B. So what this says is that B links to nothing, right? So what does this mean in terms of course pages and assignment pages?
You can't have any links on your assignment pages. You can't. Everything added that you need has to be on the assignment page itself.
Right, exactly, right? Again, this makes sense. The course page has a link to the assignment page, but then the assignment page doesn't have links to anything else. Our assignment page violates this one. Darn, right? We failed there. I'm going to fire the TA. He'll be grateful. Right, so this actually looks a little odd at first, but it makes a lot of sense. Assignment pages typically do not have pointers to other things. Okay? At least in the data set that they were learning this from, that was the case. And by the way, this rule was completely accurate on the training set, and on the test set, these were both pretty small, right? This was, back a long time ago, in the early days of the web when doing this was a new thing. But this is actually a surprisingly accurate rule. Mm-hmm.
Is that a good thing that the training set had 100% accuracy?
A good thing that what?
That it had 100% accuracy on the training set?
It's a good thing, but it's a suspicious thing, right? So another question that you want to ask yourself as a newly minted machine learning pro, right, is how much do I believe that 31 out of 31? And the answer is, well, I would believe that, plus or minus 3 or 4, which, guess what, is exactly what happens. So this is, you would have to be pretty lucky to get this right 31 out of 31 times if it wasn't accurate. Right? That's very unlikely. So I would trust this rule before looking at the test data, right? Hindsight is always 20/20. I would trust it to be accurate. I would not trust it to be 100% accurate. And that turns out to be the case, right? This rule is not 100% accurate, but it's still pretty accurate. So it's a valid rule.
It looks like the training set, the test set is just the training set in 3 more sites.
Well, again, what they did in this, problem, as you're doing in your project that everyone always, needs to do, is they split their data into training and test set, and then they were of comparable size, right? I don't remember exactly what their split was, but it's not like they were, totally different things. Questions so far? Excuse me.